Hello everyone. Hey, I'm here. Hi. uh, my name is Dubiel, and I would like to start this talk with a short note about abstractions and frameworks that we use daily. So they are great. They allow us to deliver our business value faster. They shield us from repeating the same lines of code all over again, from all the mundane tasks. But there is a dark side to them, because they hide a lot of details from us. The details that are not just some, implementation details not important to us, but the details which are really crucial and critical for the performance and stability of the applications and services that we build. And because of this, sometimes we become uncertain and very vague when talking about those, lower level things like threads. So we're not sure how they work or what happens in our application. And as Dijkstra once said, adding abstraction should not be a way to hide those things. Abstractions are here to empower us to make our language absolutely precise, to be able to speak in very precise way. And so during this talk, I would like to take a few steps back from all those frameworks and abstractions that we use, and bring back the ability to talk about threads in a very precise manner, so we are sure how they work and what are the consequences of the way they are or of the way they work in JVM applications. But before this, short introduction. So I'm a technical team leader at Allegro, and I work in a team which is responsible for building this kind of layer between microservices and infrastructure. So we have a lot of microservices, a lot of people working, and my team is there to make the life of developers easier. And so let's get to the very beginning of things. So whenever you start a new application, a new process, it's like a big bang. Out of nothing comes something. And in this very short few moments in the very beginning, there's a lot of going on there. Like there are a lot of threads created, there are a lot of things on the CPU. But after a while, it all goes quiet. It all calms down. So our application, is in its stable state. It's already processing the traffic and nothing much happens. Maybe from time to time there's like a supernova, there's a new thread created somewhere, but it's not happening so often. Everything starts in the beginning. And to give you a better understanding of what happens whenever you start a new application, I've created a kind of a test application based on Spring Boot. And I created a timeline of threads creation. So you can see the first 25 seconds in the life of this application. And you can see the threads as they are being born. Each of those blue dots is one thread. And to give you a better understanding of how many threads are there, this is the same data, just plotted in a slightly different way. So in the very first few milliseconds, there's like 20 new threads created. After a while, there comes more. It's like 30 of them, around 7-second mark. And then after a long, long time, around 25-second mark, you can see there's like 80 new threads created. Why? What happens at those moments? So we have this big bang. The JVM starts. This is the 0 point. This is the beginning of our universe, of our application. Well, the first 20 or so threads are different virtual machine JVM threads, and we're going to talk about them a bit later. Then, around 6-7 seconds in the application lifetime, Spring Context boots up, and it adds another 15 threads. So these are HTTP server threads, maybe database connector threads, things like this. And then the traffic starts flowing. And then we get the huge surge of new threads, around 80 of them. So just for the purpose of this talk, the delay between Spring booting up and thread and the traffic that starts flowing is a bit, bit longer. It takes a bit longer than usual. I just made it like this so you can see the huge surge of threads. Usually, the traffic starts flowing as soon as your application boots up, so those threads would be created somewhere probably around 10-second mark. So what happens at the very beginning, whenever the process is born? I'm going to talk exclusively about Linux systems. So, and in Linux, all threads are gathered into kind of a tree structure. So there is a process tree. And you can trace any single process going back to the first process ever, to the root of all processes. And in any modern Ubuntu system, it will be systemd. But it's always a process with a PID, or process ID, number 1. And out of it stems all the tree. And in this slide, you can see just a small chunk of a process tree. And in this process tree, you can see that I had a SSH daemon working. And I actually SSH'd onto the machine. And because of it, I created also a new shell, bash, interactive shell for my process to run. But what would happen if I run simple code in this scenario? So whenever I run Java version, I'm just going to get a new process, a child of my bash shell, which is simply Java. Well, of course, you might have a setup like this, so your systemd might be responsible for managing your Java threads, but it doesn't change much for us. But what is the process? I probably said this word like 20 times up till now. So you can think of a process as nothing more than just a collection of threads, a set of threads, which all can operate on the shared memory. So just a bunch of threads, some memory, and they can all, share the memory, mutate it, read from it from the same address space from memory. And it's nothing more. It's nothing sophisticated. This is a process, just a set of threads. Okay, but this is how processes look like from the perspective of our operating system. So what does it have to do with threads in JVM? Well, we're going to find out. So I use the ps3 command to plot this kind of a process tree. And I hid a bit of a very important detail from you in the slides before. So this is the full process tree whenever I run Java application. And you can see the same Java process here, but then there are some weird things next to it, like a new branch of things, but they look different because their names are in curly braces. You can see that the numbers are still in the same number space, but they are a bit different. What are those? Well, it turns out that JVM threads are actually system threads. So what we can see here are threads that our Java process has spawned. So what does it, and if you don't believe me, you can just go to the Java source code, and this is Java 10 source code, and whenever you create a new thread, you're going to call pthreads library, pthread create function, and it creates a new thread. It goes to the system, asks it to create a new thread for me, and we receive a new thread for this process. So what does it mean for us? As you could see, I could see Java threads in using the system tools. So if I can observe them using system tools, it means that I gain a lot of new tools and ways to observe my Java application. Not only Java-specific things, but also system tools, and there are a lot of them. If there are system threads, it also means that it's not the JVM that's responsible for scheduling CPU time for them. Actually, JVM has nothing to do with it. It has no say in this process. So Linux kernel scheduler is responsible for scheduling, for giving slots of time on the CPU for scheduling all those threads, not Java. It has nothing to do with it. So if they're observable using system tools, well, let's try them. Let's try to make some use of it. So you know the /prods file system. All the information about running processes are there. And if threads come from the system, you can also find those information in prods file system. So whenever you ls prods pid task directory, you're going to see all the threads that are running inside this process. If they are there, it's also possible to take a look at them with a higher level tools like PS. Or if you don't like PS, you can use top. But the threads are still visible. So you can do it with the -h argument. It's going to show all the threads for this given process. But how can we make some use of it? So in the PS command, I wanted to output very specific columns. So I'm outputting PID, TID, I'm going to talk about those in a moment, memory, CPU, and time and command. So what is this PID and TID? PID, process ID, I have already said it. It's just a ID of the process, of the parent process. TID is thread ID. This is the native system thread ID, the number of the thread. But how can we make some, how to use it in practice? What can we do with this information? So you've probably seen, things like this. So like all the CPUs are utilized in 100% and nobody knows what's happening. How to be able to quickly tell which threads are using up all the CPU time? Well, we can use stop or PS to see all the processes and how much CPU are they using at the given moment. So after running this command, I'm going to see this output. And you might already notice that there are 4 threads here which actually utilize a lot of CPU, like 30% each. And we also have their IDs. So this is the TID of those threads. If only there was a way to match system identifications, IDs, with JVM threads. Because, well, as much as it might be useful to know that there are only 4 threads which take up all the CPU time, I still don't know what are those threads doing. Which ones are they? So in Java world, whenever you want to talk about threads, you're going to start with JStack. Yeah, so to see the threads which are currently running in your Java machine, you're just going to use JStack with PID. Actually, well, you might want to use jcommand with thread print, whatever. But you're going to get the same output. And for each thread, in the output, you're going to see this line. And there are a few important things in this line, and I'm going to zoom in on them. So what we have here, the first column, is thread name. So if we took care of it and actually named our threads correctly, we might get some usable information from there. The next one is TID, which is thread ID, and there is a need, which is native ID. So it gets a bit complicated here. So we have some crazy TID, which looks totally different from the TID that we've been observing before. Well, this is because, this output is not so easy to read. This TID here in JStack is actually the hexadecimal representation of pthreads ID. And it's not really usable for us in the context that I'm talking about. So I just wanted to show you that the names clash, but it's not really important for us. The important bit is NID, need. This is actually the hexadecimal representation of system or OS thread ID. Yeah, so we take thread ID, make a hex of it, and it's going to be here. Well, so there is a link between those two numbers, system thread ID and Java NID, JVM NID. So let's try and figure it out. So let's take this one thread. It's taking up 30% of our CPU time, and its thread ID is 8521. Okay, So what I would do next is I would translate this 8521 into hexadecimal number, which is 2149, and then just run JStack and grep it. Grep in search of this 2149. And what I'm going to see is this. No surprise here. Actually, this was a GC thread all along. Parallel GC thread was eating up all those resources. And I can see it because the native ID need here matches the thread ID from my operating system. So you might want to probably write a script for it because it's pretty complicated, and whenever you've got downtime or something bad is happening, you're probably too stressed to remember about all those steps. But there is good news. So in Java 8, there was this method which was called setNativeThreadName, and it is called whenever you use thread.setName. Unfortunately, it was not implemented. You can see not implemented yet, because with Java 9 comes the implementation of this method. So if you need any more reasons to update, there is another one. And what it does is it actually takes first 15 characters of the thread name whenever you set the thread name, and it broadcasts it to the p threads. So what's happening is that your system is becoming aware of the Java thread naming. So it's only 15 chars because it's like 16 chars limit plus 0 at the end. But this is a very powerful tool now, because what we're going to see in each of the system tools, like PS3, is actually the names of the threads. You can see them here. It's not Java anymore, some cryptic name. It's the name of the thread. And it's the same in PS. So if I were to say which thread is taking up all this CPU time, it's easy now. I can see it GC. I don't have to do all this crazy hexadecimal mumbo jumbo. I can just go with the output from PS. So unless you have really long thread names which often clash, this is a great tool to observe what your application is doing. Yeah, so it's just the GC thread. So we already know that JVM threads are actually system threads and how to observe them. And there are a lot of threads in a typical application. So I would say that this one, we have like 110 or 115 threads here, is actually like pretty small. So you could see like applications with 500 or thousands of threads written in JVM, in Java. So let's take a moment here and wonder how many threads can we actually spawn? So how expensive it is to spawn a new thread? Why are we able to spawn like thousands of them and our applications are still running? So there are different types of costs when it comes to threads. There is the explicit cost. We need some memory to allocate the stacks. It's 1 megabyte by default, and it's an explicit cost. You can actually calculate it. And there are the implicit costs. So there is a cost of context switching. There is the cost of safe pointing and GC roots. So each thread you spawn actually becomes a GC root. So whenever a GC kicks in, it has to iterate all over them and see if it references any other stuff. The same with safe pointing. So before you start your garbage collector, you need all the threads to stop at the safe point, which means that we're waiting for all of them. So the more threads you have, the more time you might be spending waiting. Okay, but let's talk about the explicit cost first. So how big is a thread stack? Before we jump into the question of how big it is, let's settle one thing. So as you all know, in Java applications have this, like 2 regions of memory. So there is a heap, and this is the kingdom of garbage collectors of managed memory, and there is the off heap. So all the other, so this is the place like we don't touch it usually. Like this is the system memory that belongs to the Java process, and thread stacks live here. They live in the off heap. So setting maximum heap size doesn't, affect the number of threads that you can spawn. And there is this cute little tool in JVM, which is called native memory tracking. And it can tell us how much memory we are actually getting from the operating system. So whenever JVM goes to the system and asks it for more memory, it's going to be logged using this tool. So it's called native memory tracking. And there are different categories of allocations, and one of them is thread allocation. So in the output of this tool, like just printing Java version and printing the memory used, we're going to see that we actually created 18 threads. This is the number of threads just to print Java version, and we actually asked for 18 megabytes of memory from the system. So after doing some maths, you can see that actually I was telling the truth. So the size of a stack by default is 1 megabyte. So one thread is 1 megabyte. Okay. So if you wanted to calculate the total application memory, the total memory used by an application, what we would have to do is actually take the heap size and then take the amount of threads and multiply it by the stack size. And there are some other factors that we should actually cover, but that would be it for us now. And based on this simple formula, we can start reasoning about how many threads can I actually spawn before I overflow the memory. So let's say I get a machine with some amount of RAM. Let's say it's like 2 gigabytes, and there is some heap, and there is the off heap or all the other memory in the system. So it's 2 gigabytes. The heap would be, I don't know, 500 megabytes, but just telling 500 feels wrong. So it's going to be 512 megabytes. And then on the off heap or on the other parts of memory, I got let's say I'm going to allocate 300 megabytes for some stuff we don't care about. And it leaves us with around 1.2 gigabyte of memory just for thread stacks. Yeah? So once again, complicated math. 1.2 gigabytes, 1 megabyte per each thread. It should give us the ability to spawn 1.2 thousand threads. Am I right? I think I am. So let's see. Let's check it. So I got this Vagrant box running here, which has exactly 2 gigabytes of memory. And there is a simple application here somewhere. Okay, it's here. It's called thread spawner. And what it does, it actually only spawns threads, and it prints how many of them it spawned. So I'm going to run it. Okay, I'm running it. Didn't I say that I will be able to create only 1.2 thousand threads? Well, I was able to create 5,000. Just to say that I'm not lying, you can see in top that I've got 2 gigabytes of memory. This is 2 gigabytes. Okay? So how is it possible? Well, you can't use all the memory if it's not real. So let's think about it. If it's not real, we cannot use it, or we cannot overflow it. What does it mean? So there are actually two ways to measure the amount of memory that the process is using. We've got virtual size and the resident size. So the virtual size is virtual memory size. It's a virtual memory. It does not exist. It's just an address space that my thread can access, that my process can access. So, whenever I ask the system for some memory, it can say, sure, here you go. You've got 10 gigs of it. It doesn't mean it's real. I just can access it. As long as I don't access it, it's not there. It might be somewhere on swap, or it might be just, non-existent. And this is opposed to resident set size. So this is the actual memory that my process is using. This is like the hard memory that I have somewhere on RAM and I'm using at the moment. So this is the only metric that can show you how much memory your process is eating up at any given moment. It contains everything. Like for Java application, it's like the sum of heap size and all the threads and meta space and everything. Like everything the process has allocated, it's in res. So let's see how it works. So once again, to my machine, and I'm going to run top here. And then I'm going to run this Java spawner once again. And you can see the virtual size is like, I don't know, 7 gigabytes or something. Oops, it's gone. While the resident size was still only 70 megs. Why? Because the threads that I spawned do nothing. They just go to sleep. So there is no need to allocate 1 megabyte of stack for a thread that does nothing. So the system just doesn't do it. It promises my process, my JVM application, that it will give me some memory if I really need it, but it doesn't have to do it. If I actually tried to, use up all this memory, like run Spring application with huge stacks, well, I would be in a world of pain. So, like, I would be out of memory very soon, and the out-of-memory killer would probably come and kill me. So, as you could see, I was able to spawn like 5,000 threads or something. So if it's not the memory that limits me, what is the limit? And here we come to the notion of those operating system limits. There are a lot of those, and they usually show up when you least expect them. The one that we're interested in is max user processes limit. So it tells us that single user cannot spawn more than around 8,000 processes. And as I said, threads and processes are not so different in Linux world. They're very similar. So, new threads actually eat up, or they add up to this limit, to this 8,000 limit. That's why I was able to spawn so many threads, because they didn't reach this limit yet. It's not because of memory, it's because of a system limit. Of course, you can change it if you want, but this is the default on Ubuntu. Okay. So, you've already seen that I can create a lot of threads, but should I? I can, but should I? Well, if you've been following the newest trends in frameworks, you can see that actually we try to limit the amount of threads. So like, here comes Webflux, which actually, instead of spawning 200 threads, it spawns like, just a handful of them. But why? Why do we strive to keep the number of threads at the low level? Well, we've got only so many physical CPUs. Like in this case, let's say we got only 4 of them. And then my application spawned like 110 threads. So it's physically impossible for all of them to run at once because we have only so many threads, so many CPUs. So what are they doing? Well, mostly they are just waiting. They're doing nothing. And let's get back to the cost of threads. I've already told you about the explicit cost, the memory footprint. But I would like to also talk about the more implicit one, which is context switching. And what it's all about, and why is it bad? So, if we take a very simplified picture of a processor architecture, you can see that you've got, the processor core, and then you've got some levels of caches, of memory caches. L1, L2, and L3 caches. And L1 and L2 cache are usually exclusive, so like they are exclusive to the core itself. L3 cache is usually shared between different cores. And why are there so many caches? Well, because you can only fit so many bytes or memory close to the processor at a given cost and in a given access time. So the closer the memory is, and you can see the access times here, the the less of this memory we have. So like for L1 cache with the access time for happy path, of course. So if we have cache hit, it's like nanosecond. It's really blazing fast. But we also have very little of this memory. It's like, kilobytes. And then we have L2 cache, which is a bit slower, but it's still like, more kilobytes. And then we have L3 cache, which is already like megabytes in size, but it's already very slow, but like much slower. It's like 20 to 40 nanoseconds. And then we have RAM. We can have terabytes of RAM, but in the time scale of a CPU, the access to RAM is really slow. It's like 2 orders of magnitude slower than accessing L1 cache. But what does it mean for us and our threads and context switches? Well, let's say a thread is running on a processor. And because it's running, it probably needs some data to operate on. And this data is called working set. So the data that thread operates on is working set. And there's usually some limited amount of data. And, well, very rarely you would see a program which is able to fit all its working set inside L1 cache. So usually like the data flows from L2 to L1, sometimes maybe from L3, sometimes from RAM. But, we just keep it close. We keep all the data close. And then comes another thread, and system scheduler says, okay, now you're going to run. So this is another thread. And you know what? All this data that we've been fetching from RAM and keeping close is probably useless now. I mean, it's not stale. It's still good to go. You can still use it, but you probably don't need to, because threads in Java applications, they tend to operate on different sets of data. So it's probably different HTTP requests coming in, and it has totally different data, and it uses totally different data from the database. It's just different data. So this thread, whenever it comes, has to fetch all the data from RAM once again, just to keep it close. So the real cost of context switching is actually, in terms of whenever we switch threads, is not really the context switch itself, is the missing opportunities of using the data that you had very close to you in the caches. So you can say that the cost, the worst case scenario is like maybe 30 microseconds for each context switch if we're not reusing any data. But it's not easy to reason about it. Well, because as I said, it depends on the data. If data in caches is usable by different threads, then the cost is smaller. You can observe it actually using system tools like perf. So with perf, you can see the amount of context switches, but also the context hits, the cache hits and cache misses. So we can see if you're actually reusing the data, if your threads can use the same data, or there are so little threads that there is no need for context switch at all. So this is the implicit cost. That's why we try to do this. Like, if we have less threads, there will be less context switches, so profit for all of us, for our performance. But let's get back to our application. So we've been talking about some low-level details. Let's get back to the application itself. So as I said, first, the VM threads come to life. And let's see, what are those VM threads actually? So this is a zoom in on the first 100 milliseconds in the application lifetime. And guess what are the first 2 threads that come to life? It's garbage collector. So before we start mutating, before we start doing anything, we need somebody to clean it up. So the GC threads are born. Then we've got the VM thread. VM thread is a very specific thread because whenever you need something from the virtual machine, you're going to put a task on the queue, and this thread actually reads this queue all the time and just does these tasks. It's like if you want to go to the save point, you're going to ask this thread to do it. And then we got JIT compiler threads, C1 and C2, and then some other less important. Okay, what comes next? Spring Boot context and traffic starts flowing. So why is there so much space between Spring context booting up and traffic starting flowing? Like, why are there so many threads created? Why are those threads created not here, but here? And how can we manage them? How can we utilize them to their full potential so that our application is actually very performant and stable? Let's talk about managing threads. So basically, there are two ways of creating threads, of using threads. You can either do the new thread, meaning just create a new thread, run something, and throw it away. Or you can use thread pools. You've probably seen this construct, this method, executors factory, executors fixed thread pool, to create a thread pool of a fixed size. So, as you might suspect, or as I already told you, creating a new thread has its costs. So probably we don't want to use it. We would like to, as with all resources that are costly to create, we would like to pool them, keep them in pool, and cache them for later. And a small notice, like be careful who you trust. So if you use Spring at the moment and you use annotations like @async or you use async REST template, what you're going to get under the hood is this thing called simple async task executor. And what it does is that for every task that comes up, it fires up a new thread. The number of threads is unlimited, and it does not reuse threads. So it's just like calling new thread. And actually, there are some pretty great people working at Pivotal, and Marcin Grzejczak is one of them. And the first time I showed this presentation, he came up to me and told me, Adam, if you don't like it, let's change it. If you have reasons for it, let's change it. So it works like this, but I hope we will be able to change it, to come up with some better solution. And it's up to me now. So I feel bad by showing this slide, but I have to, because it works like this for now. But we're going to create a new issue, and I'm working on some set of examples why it is bad and how can you avoid it, and why is it actually a very common thing to kill your application by using this. So anyway, let's get back to thread pools. So thread pool is a very simple concept. Like you get some resources and you just want to cache them. But what happens when the thread pool becomes full? So you got 10 threads or 8 in here, or sorry, 6. You got 6 threads and all of them are busy and new task comes. Well, as in all of pools, usually there's some kind of a queue. The only question is, how big is this queue? How much tasks can you actually store in this queue? And the sad answer, by default, it's infinite. And by infinite, I mean it will overflow your memory and your app is going to die. So this is what infinity means. And to be able to actually, change it, what you have to do is you have to stop using the executors factory and use the implementation of thread pool in Java, which is thread pool executor. And it has some interesting arguments here, constructor arguments. The one here is task queue implementation. So you can add any task queue here, which can be bounded task queue. Like you can just set the size of a task queue to 100 or 1000. It's up to you to measure, to calculate how big should it be, but it's not infinite. So it's not going to crash your application. And with this comes another important property, which is rejection policy. And rejection policy is a piece of code which is run whenever your queue fills up. So let's take a look at it. So the happy path for us is that we have some thread which tries to submit some task to the thread pool. And it just puts a new task. Everything is fine. And, it just gets executed on the thread pool here in those threads. And everything is great. Well, if we use the default settings and we get this unhappy path, so everything is clogged up and we have no resources, what's going to happen is that whenever a thread puts some new task on this queue, well, we're not going to get any feedback. Everything's going to be fine, but the queue is going to keep on growing, as I said. So because the size is infinite, it's just going to keep on growing. Well, this is a bad situation for us because, well, the memory is finite, unfortunately. So if we use bounded task queue, we can also take advantage of different rejection policies. And there are a few of them which are pre-implemented and available in JDK. So one of them is caller runs policy. So whenever the queue is full, instead of switching the context and putting the execution into the thread pool, the thread which wanted to call the thread pool is going to run it itself. So it's going to block more. It might not be ideal for a lot of cases because we actually wanted to offload the work, but it exists. Then the other one, which is actually the default, is abort policy. So whenever the queue is full, it's just going to get an exception. That's great. We failed fast. We know that something wrong is happening, and we can handle the situation. So we get a quick feedback. This is really great. There are also some more sophisticated policies, like discard. So if you want to put the task onto the queue, well, it's just going to put it in dev null if it's full. Like, it's just going to vanish. Well, it might be useful in some cases. And the other one, which is discard oldest, it's very similar, but whenever you put something on a queue which is full, instead of discarding your task, it's going to discard the oldest one, you know, the first one, waiting for execution. And if you have tasks that are actually, you know, that become stale very quickly, you might want to use it. And of course, this is a very simple functional interface. It has only one method. So it's very easy to implement your own rejection policy, and you can do things like measure how many tasks are you actually losing, or I don't know, put the task somewhere in memory or in the database. Depends on the need. So this is a very cool tool, and if you have bounded queues, you should use it. If you had unbounded queues, well, it will never run. So, okay. So we created a new thread pool, and still, it doesn't answer the question, why are all those threads created so late? So my context starts here. All those threads should be created here, right? Because the thread pool is created here. Well, not really. By default, whenever you create a new thread pool, it's actually empty. There are no threads in it. Only as the tasks come in, the thread pool fills up with new threads. Whenever a thread is done, it's not destroyed. It's cached. It's still there. But it's not created eagerly. It's created lazily. If for some reasons we wanted to have all the thread pools ready whenever we create them, we can use this thread pool executor method, which is called pre-start all call threads. So if we run it, we're going to get all the 80 threads at the very beginning whenever the thread pool is created. And so, well, important question is, this is a cool graph, but yeah, like this is a graph for some dummy application. How can we see how my application behaves in production? What tools did I use to create this? Well, there is another cool thing that comes with Java 9, which is called like JVM Unified Logging. And with this, you can just log the threads. You can easily log threads lifecycle into the file. It's virtually for free. So you can just dump the information about each thread being created and each thread dying into the file. And based on this output, you can create things like this. So the key takeaways from my talk are JVM threads are actually system threads. And this means that we have amazing tools to reason about what's happening inside our JVM. We have a lot of system tools which can help us visualize and diagnose what's happening inside. We're moving towards things like Webflux, which actually try to spawn less threads, because less is more, because each thread costs, and the costs of operating many threads can be actually huge. And whenever you work with a thread pool, whenever you think about threads, well, try to tune your thread pools, because by default, well, you might run into some weird corner cases. So that's all from me for today. If you would like to ask me some questions or follow me on Twitter or work with me, here are the details, and I'm happy to take any questions. Thank you.